In this video, I'm going to show the image of why you need the internal built-in eye monitor and a receiver of a SerDes system. Before looking at the built-in eye monitor, let's look at the eye diagram and the transmitter of a SerDes system. As you can see, the eye diagram can be measured through an oscilloscope directly at the TX output, which will show the signal integrity SI before a channel. Again, to meet the bit array at the target level, the most standard will define the eye mask to identify if the TX SI performance is acceptable for the link budget across any third-party SerDes. Two eye diagrams images are shown here for your reference. The red one obviously shows the small opening and violates the standard eye mask. On the other hand, the green one obviously shows a wide or big opening and meets the standard eye mask with a certain margin. So, which one could meet the low bit array easily? Since the bit array image is obvious, I don't need to tell you the answer now. Can you measure the eye and the receiver through the oscilloscope directly? Any circuit images? Bingo! No matter the CTLE output or DFE output, since those nodes are inside the chips, that's difficult to access the eye information inside the RX. So, for testing purpose, that's an obvious image of why you need the internal built-in eye monitor and receiver of a SerDes system. Here is the eye monitor image you may have for the RX testing nodes at either the CTLE or DFE outputs. Looks like we resolved the testing issue at the RX side, and we can monitor the receiver performance either at the CTLE, DFE outputs, or other nodes you want. But do you see any degradation images here? Correct. Bandwidth reduction. As you can see, the eye monitor may need to connect to the pop nodes. Unfortunately, the input device and parasitic capacitance of the eye monitor will slow down the pop node. In addition, those are high speed and critical nodes and very sensitive to any extra capacitance, which would degrade the eye's overall bandwidth. Any circuit image of the bandwidth degradation issue here? Right, CTLE. As you can see here, without the eye monitor, the CTLE's high pass response and the peak frequency were in the right spot to equalize the channel's low pass response to an overall 5 GHz bandwidth properly. But if the bandwidth drops, the high pass response and the peak frequency of the CTLE will move to a lower frequency, such that the CTLE cannot equalize the channel's low pass response well, and the overall bandwidth will be less than 5 GHz to increase the bit array. Any other images? Bingo! DFE's timing constraint. As we discussed last time in the Why Not DFE Only video, the DFE's first sampler needs to take any tiny input swing to convert or regenerate to a full swing by the positive feedback. Therefore, a simple delay image here reminds you that the bigger input swing may take a shorter time to reach the full swing at the output. But if the CTLE's degraded bandwidth cannot open the eye at the DFE's first sampler big enough, the sampler time delay would be too big to meet the 1 UI timing constraint. What else timing degradation image here? Yes, the summing node or DFE's output settling time. Like the CTLE, if the eye monitor is connected to the DFE's output y of t, then the summing amplifier's bandwidth would decrease, and the aggregate summing time would take too long to meet the 1 UI timing constraint as well. Here is a current image of the summing node's settling behavior, and we want the complete switching time would be as early as possible. In addition to the testing purpose, why do you need the internal built-in eye monitor? Any system image, for example, unknown TX output swing, unknown channel loss, unknown CTLE gain, and lots of other unknown settings. Or any circuit image from the error slicer. Bingo! The eye monitor result can be used as a criterion of the adaptive application in equation. As we discussed in the Y sin LMS adaptation video, the sampler only samples the voltage level at the middle of the eye through a CDR's lock phase. So, in addition to the vertical eye height, the eye monitor will have extra eye width information. Overall, the samplers may be able to choose an optimized phase to reduce the bit array further if the middle of the eye is not optimized. It looks good, but do you see any implication images of such eye monitor approach? Bingo! The converge time could be a concern. As we discussed, when a link starts up, most standard or protocol may require limited training time to start sending the data. So, the evaluation time could be too long to meet the required training time. As you can see, in addition to the vertical voltage can be swept, the horizontal phase must be swept too. To have a meaningful resolution, the number of phase swept usually was chosen to be 16 or 32, which would increase the measure time by a factor of 10. So, the eye monitor assistant adaptive equation could be an option, but require a further optimized algorithm or approach to reduce the converge time. After we understand why and the limitation of the eye monitor's usage, let's look at the eye monitor's circuit image further. First, the vertical voltage scan can be done by any voltage offset added at the sampler input. So, more error will show up if the offset H0 on both sides are too big. Similarly, the horizontal phase can be done by any phase movement swept at the clock sampling phase. So, more error will show up if the phase code is chosen at the data transition or eye boundary. Here is an interesting image I found on this website. Their internal eye monitor shows how the eye took at the DFE's output Y of t. Interestingly, the eye is totally closed after the DFE if the data went through the TX 26-inch channel and X without any equation. But with the TX FFE and CTLE, you can start to see the open eye. Furthermore, the DFE would open the eye even bigger at both the eye width and eye height. Of course, we don't know if they apply the eye monitor to the adaptation, but the internal eye can be observed through the internal eye scan for sure. Here is the summarized image you may have for why you need the internal built-in eye monitor at the receiver of a storage system. Like the TX outputs, the objective is to have a big eye opening or eye area, such that the bit array can be reduced as small as possible. However, the eye's internal eye cannot be measured directly through any external probe. So, an on-chip built-in eye monitor is a must for testing purpose. Since the eye's internal eye or SI is available, The equation adaptation can be done through the built-in eye monitor if the converge time isn't a concern through a careful design. No matter what the usage is, the eye monitor's loading effect will degrade both the eye's performance and the pop circuitry, and the pitfall must be mitigated carefully. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may benefit from it.